So this video will be some feedback for a Year 10 practical, Year 10 Physics practical. This is on Ohm's Law, so it's quite a classic practical. I'm going to tell you some of the things that these three students did really well and a couple of things that maybe their next steps are. But these are all really nice examples of some people who have worked hard on this and produced a lovely experiment write-up, so well done to them. So this student starts with a bit of an introduction. Okay, I like the way he's talked about the volts to amps ratio. Okay, he's actually applying Ohm's law, which is V equals IR. So volts to amps means V over I. It's good that he's talked about ratios in there. Okay, he's identified that here as well, using the units rather than the symbols, but that's okay at this stage as well. He's correctly identified the independent, dependent and controlled variables, which I think is really, really good. Referring to them, I've told him here is current in amps, potential difference in volts. Then the, that's here. Then the experiment is very nicely presented with a diagram, okay, and a method. And he said that what he's going to do is change the resistor for a bulb and investigate the difference between them. Okay, he's got a risk assessment. I think one thing that he's missed maybe is that the resistor gets really, really hot. Now he's done his sketch graphs here, which sort of surprised me because over the page are his real graphs, which are really, really quite well presented as well. He doesn't have units on his axes, but he does have a line of best fit here. And he can talk about the difference between the resistor being a straight line and the bulb being this curve here as well. Now, the next step for this student, although he does have a really valid conclusion, where he talks about the more volts meaning more amps, okay, so, and that being a fixed situation in the fixed resistor, and not quite being the same in the bulb, and he talks about the next thing to do is do more than one resistor, so do the next resistor, which is great. That's definitely the next thing he could do. Also, what I would have really liked to have seen is him using his graphs to calculate a gradient, and a gradient is the height of a line divided by the width of that line. So you make a little triangle and you do the height over the width. So the gradient is the resistance, which is V divided by I. So that would have made a really strong conclusion. But as you can see, it's a really nice experiment with lots of positive points, and that he's worked hard on. He's just moving up that skill level from applying himself to it to really doing the analysis on the graph work. Very well done. The next one is an interesting one as well. It's well presented as well. It could really do with what the other chap had with an introduction and a prediction. But I like the way that this student has presented her tables here, okay, with correct headings here as well, which is great. The graphs then, and this is where this one really comes into its own, are actually calculated, they're actually plotted on Excel, which is a really useful thing. It's time saving, but also you get a very high degree of accuracy because the computer doesn't tend to make plotting errors. And what this student's done is actually shown on the graph how those gradients here have been calculated. Okay, brilliant. And she said this one's proportional, which is what I would expect from Ohm's law, V against I. Okay, and down here, not quite as proportional, but still this is the bulb here, and she's used that to calculate a gradient. Okay, what I've just indicated for her here is that she should use the line rather than the points. And this one with a bulb, we were expecting a curved line. So she should really have been expecting that from her prediction, if she'd made one, and that would have meant that then she could have done the analysis on that, and then she would have been talking about a gradient here and a gradient there. There's another little shortcut with Excel, because actually Excel will display an equation for you. This says y equals 6.609x plus 2.4163. So what this shows you is actually y equals mx plus c, which you'll know from your maths is an equation for a straight line. And that's a really crucial skill in physics to understand how this equation from a straight line relates to the physics. Well, m, the number before the x, the coefficient of x, that number is the gradient. So actually, we can calculate gradients from the computer to a very high precision without making that effort, but I love the way they presented this. And then this goes on to talk about a motor, and the motor did something really interesting for this student and actually got her really thinking about why the motor is not even increasing as you increase the voltage, why the current is not always increasing. You've got this random seeming scattering of points down here, and then at a very low voltage, the highest current, and that's the interesting thing. And she goes on to talk about that in the conclusion. The conclusion is very methodical, and she's talked about it might be the heating, okay, or in the motor. She's even plotted another graph thinking, well, is it because the time the motor's been left on for? Okay, so she's thinking about that. And she said, well, there's more work to be done on this. There's more I can actually do on this. The other thing I think is very nice about this is actually including that conclusion next to the graph. Makes it a very methodical, systematic type of conclusion this student's done. Very well done to them. Then the next one, this one is the exact same experiment. Okay, this time it's exclusively done on the computer. Okay, lovely setup, right up, risk assessment, full risk assessment. Maybe the risk assessment could have an indication of how risky each step was. Some excellent detail here of what the things are used for, what size of resistors you need to do this, what the range of the power supply needs to be. I think that's very, very nicely done. Again, a really great effort presenting the data in the tables there. A good sort of preliminary conclusion before she's plotted the graphs. Then this is, I think, this really is good. This is the graphs all plotted on the same set of axes. And what that's allowed them to do is actually compare the gradients directly. So actually the 100 ohm resistor, you can see, has the highest gradient, it's the steepest line. The 22 ohm resistor is shallower, and the bulb is much shallower but also changing. So this plotting these on the same graph allows her to compare them directly. And then as we go forward, the conclusion is not short, it's step by step. She concludes for the first resistor, the 100 ohm resistor. She tells us what the graphs are showing here and how you calculate the gradient in here as well. Concludes for the first resistor. She's missed out a 0 there, so she's got an order of 10 error there, which is just a sort of learning point, especially for exams. Check your answers are kind of in the right range. So a 100 ohm resistor was expected, 13.3 was calculated. Maybe that's not quite in the right range, but she's done the correct thing for the next one as well. So what I think she could be thinking about is, well, why are these both above the range that we were expecting? Okay, they're not much out, but why are they both above the range? Okay, that's very interesting. And then what she's done interesting here for the bulb is she's calculated the gradient at a low voltage and the gradient at a high voltage, which shows that the resistance pretty much doubles between 3 volts and 8 volts, which is very, very interesting indeed. And that is about this flow of charge creating a heating effect, and that heating effect actually causes a higher resistance. So I think this is a very excellent piece of work. I think that the student has really thought about it, they've taken their time, they've been very systematic in their thinking. They've even begun to use words like this. If we could have done each resistor more often than once to get a reliable set of numbers. Okay, so when evaluating, it's very useful to be thinking quite precisely about what language you're using. So are you commenting on how reliable your experiment was, how accurate it was, how precise it was, and was it valid, was it a fair test? And lastly, the golden challenge, what does it mean in a context? What's the point in doing this science? It's not just for us understanding Ohm's Law. Ohm's Law has a very, very useful application in the real world. In fact, loads and loads and loads of useful applications in the real world. So well done to this class and all the Year 10 who've done this practical. And these are just a few examples of some really high quality work.